Hey guys, my name is IBM and I want to take you to the last part or the last episode of Deformation of Solids. And remember, this is AS Physics. Do not forget to share the videos. You can write a comment. I'm always willing to try and rectify or correct whatever is whatever is really not clear. I'm always willing to try and rectify it. So without wasting time, I want to take you to the introduction. So remember, this is the Cambridge International Education. Okay, so remember this is the formation of solids, and I think this is going to be lesson 2. And lesson 2 is going to be the gist of this unit. Lesson 2 is the most important part of the formation of solids because in lesson 2 we explore stress, strain, Young modulus, and elastic potential energy. Those are the most common concepts in the formation of solids. So let us go into stress, strain, and Young modulus. So let's begin with the meaning of the term stress, or which we shall sometimes call tensile stress. So when somebody talks about stress on a material or tensile stress, we are referring to the ratio of the force the ratio of the force per unit cross-sectional area acting on a material. That is what we call the stress on a material. So you may relate stress to pressure, but the difference would be that stress um, does not mind about the force being perpendicular to the surface or the force being perpendicular to the cross-sectional area. Unlike a pressure, where for pressure, the force must be acting perpendicular to the area. That's why pressure is defined as the normal force per unit cross-sectional area. So stress on a material is defined as the ratio of the force per unit cross-sectional area, or the ratio of the force per unit cross-sectional area. When I say ratio of the force per unit cross-sectional area, it's like I'm making a repetition because the ratio itself is equivalent to saying per. So it's simply the force per unit cross-sectional area. So it is actually a measure of the force required to cause a particular deformation. That's the meaning of stress. How much force is required to cause a particular deformation? That's what we call um, a stress of a material. It is also a measure of how strong a material is. How strong is the material? In other words, if a material is very strong, it would require more force to cause a particular deformation. So from the definition of stress as force per unit cross-sectional area, we shall always use the letter sigma to represent force. We shall use the letter sigma to mean stress. This is read as sigma. We shall always use sigma for stress as the force acting the force per unit cross-sectional area. In an exam, you can just write the definition of stress as force over cross-sectional area. You don't write F over A, but you write force over cross-sectional area. And because the units of force are newtons and the units of area meters squared, it means the units of stress are going to be the same as those of pressure, which are the pascals. Therefore, stress is kind of similar to pressure because they have the same units since it is force over area, but I have explained how stress is different from pressure. For pressure, the force must be acting normally to the area, but here we just need how much force is required to cause a particular deformation. So we don't mind about if the force is acting normal to the area or at an angle, whatever. That is what we call stress. On the other hand, we have what we call a strain of a material or tensile strain. So strain is the ratio of the extension compared to the original length. It's actually a measure of how much a material is being stretched. That is now strain. The other one is a measure of how much force is required to cause a deformation. And this one is a measure of um, how much a material, a measure of how much a material is being stretched. That is in comparison to its original length. Therefore, it is a fraction it is like the fractional increase in the original length of the material. That's what we call the strain. Fractional increase in the original length of the material. Therefore, since it is extension of the original length or the change in length over the original length of the material, then we shall write strain as extension divided by original length, or you can use E over L naught, where E is the extension, or delta L over original length, where delta L could literally stand for new length minus the original length, which is the same as the extension. So that's what we shall call the strain of a material. So I want you to always note that always both extension and original length are going to be in the same unit in order for us to compare to obtain the fractional increase. We cannot obtain the fractional increase without ensuring that the strain, I mean the extension and the original length are in the same units. Therefore, you need to note very carefully that always the extension and the origin length should be in the same units. And because the extension and the origin length are in the same units, it means the units for strain is going to be a quantity without units. Therefore, we can say strain may not be considered a physical quantity because a physical quantity, as we shall see, or you might have seen in the first unit of year 12, that is physical quantities and units, a physical quantity must have units and magnitude. So that means the strain is just a magnitude, therefore it has no unit. It is just a measure of how much a material is being stretched. That is the fractional increase in the original length of the material. Therefore, strain is not a physical quantity because it has a magnitude but it has no units. So it is going to be either expressed as a fraction or simply as a percentage which has no units. That is going to be the strain. Then on the other hand, I have also mentioned Young modulus of a material. And now Young modulus is going to combine the two, stress and strain. That is going to be the Young modulus of a material. So the Young modulus of a material is the ratio of stress to strain. In an exam, you can simply write Young modulus as stress divided by strain. Remember I said the stress is sigma. Of course, strain is going to be represented by the letter epsilon. This is epsilon. Some people read it as summation, but that is epsilon or epsilon, depending on where you are from, where you come from, or depending on which kind of English you are actually considering, or which kind of English you speak in your country. Could be it American, could it be British, and so on and so forth. So Young modulus is stress over strain, which is going to be sigma divided by epsilon. Now, if we combine, sometimes students prefer to use Y for Young modulus, but commonly E is going to be used, capital E is going to be used for Young modulus. If we combine the definitions of stress and strain, we shall come up with a simpler expression that Young modulus E is going to be equal to F times the original length of the material divided by A times E. So many times in the calculations, students will always use Young modulus as force L naught over A times E. Note that A is the cross-sectional area of a material. Many times the materials have a circular cross-section, and in that case, if the material has a circular cross-section, then the area is going to be pi r squared. And sometimes the diameter is given, and because diameter is equal to radius times 2, it means radius can be diameter over 2. So sometimes the cross-sectional area will be quoted as a pi d squared divided by 4. So do not forget that every time you are dealing with Young modulus or stress, strain, and Young modulus. Okay, so we shall just define the quantities involved here. Number one, we have that F is going to be the applied force. L naught is going to be the original length. So this is L naught, original length. L naught is going to be the original length. And then A is going to be the cross-sectional area. A is going to be the cross-sectional area, and E is going to be the extension of the material. So that is Young modulus. So Young modulus would have the same units because we notice that strain has no units. And to find Young modulus, we are dividing stress by strain. That means the units of Young modulus are going to be the same as the units of stress, which means they are going to be the same as the units for pressure. So Young modulus will have the units the same as those of stress, which is newtons per meter squared. And of course, this is the same as the Pascal. Newtons per meter squared is the same as the Pascal. So they have the same unit as those of stress. However, one important thing we need to note is that many times Young modulus of materials are very large, that they are going to be quoted in units such as megapascals or gigapascals. They are of order mega or gigapascals. And of course, we know what mega stands for. This is 10 to the power of 6, and giga stands for 10 to the power of 9. So many times Young modulus will be quoted as megapascals or gigapascals because they are very large. They are always very large values. So that is a good introduction of stress and strain. So let's now think about a graph of stress against strain. So to fully understand the concepts of Young modulus, stress against strain, since we saw Hooke's law, that whenever a load is applied to a material, the load causes an extension, and for small extensions, we saw that the load F was directly proportional to extension. So for small extensions, the load is proportional to the extension, and if we have that Young modulus is the stress against stress over strain, it means we can sketch a graph of stress because stress is how much force is required to cause a deformation, and we can sketch a graph of stress against strain, and because stress would be equal to Young modulus times strain, it means we can find the Young modulus from a graph of stress against strain. We can find the Young modulus from the graph of stress against strain. Therefore, a graph of stress against strain is going to be very, very important. But a good student should be able to notice that the graph of stress against strain is mostly going to be the same as the graph of force against extension. Let's try to explore this in more details. If stress is equal to Young modulus times strain, and stress is force over area, this should be equal to Young modulus E times strain, which is extension over original length. Now I want you to notice that when a material is stretched, the change in cross-sectional area is extremely going to be small. But because original length is constant, then it means like the force is varying directly proportional to the extension. Because the original length of the material is constant, and the change in cross-sectional area for a material which is being stretched is always very, very small and almost negligible. In other words, the area plus the change in the cross-sectional area is approximately the same as the original area of the material when it is being stretched. So it means cross-sectional area is almost constant when a wire, for example, is stretched. Therefore, if I sketch a graph of stress against strain, it is almost the same as the graph of force against extension. So the graph will take the same shape. Therefore, a graph of stress against strain is going to take the same shape as the graph of force against extension that we talked about in lesson 1. So the graph will look like that, and it's almost the same shape as the one that we saw in lesson 1. So the graph is going to be the same. So just talk about a few things about this graph. Number one, you will notice that there will be a point where the graph is a straight line, say from O to P, because here for small loads, the load is directly proportional to extension. So here we say Hooke's law is obeyed. So this is Hooke's region. Hooke's law is obeyed up to point P. And if Hooke's law is obeyed, then it means we are going to find that is the only point where we have a straight line. That's the only point where stress is directly proportional to strain. And when stress is directly proportional to strain, then we can find the gradient of the graph. And the gradient is going to be equal to the Young modulus. So the gradient of a graph of stress against strain is going to be the Young modulus, which can be got from the straight line part. After all, we saw that stress is equal to Young modulus times strain. So if I compare this with y equals to mx plus c, there is no y-intercept because when there is no stress, there is no strain. So the graph goes through the origin. But on the y-axis, I have the stress. On the x-axis, I have the strain, which means the gradient is going to be the Young modulus, only for that point where stress is directly proportional to strain. Beyond point P, the stress will not be directly proportional to the strain because the extension will no longer be directly proportional to the load. But the material can return back to its original length if the deforming force is removed. However, after point E, which we call the elastic limit, we call this one the elastic limit. So after point P, when the deforming force is removed, the material does not go back to its original length. The stress is no longer directly proportional to the strain. Therefore, we call this point, after this point, we undergo what we call a plastic deformation. So this is called the plastic region. That is called the plastic region. Up to point E, we have what we call the elastic region. So here the molecules which make up the material slide past each other, causing a permanent deformation. So the material is permanently deformed by the stress which is being applied at that point until it reaches the fracture point. Fracture is the breaking point until the material breaks. So we can simply say that in the linear section, stress is directly proportional to strain. That is where we have a straight line. Thus, force is directly proportional to extension. That's why I said in that region where we have a straight line, Hooke's law is going to be obeyed. So in that region, Hooke's law is actually going to be obeyed. A few things we need to note from what we have just discussed. Number one, a spring constant varies for a spring of the same material, but with the different dimensions. If we consider a spring, we know that force is equal to K times X, where X is extension and F is the load. We can have springs made up of copper, for example. That means the material is the same material, springs made up from the same material, copper. But they could be having different values of L, length, or they could be having different thicknesses. And if the springs have different thicknesses, then the spring constant will be different. However, the Young modulus is constant for a particular material irrespective of the dimensions of the material. As long as the material is copper, for example, if we have two springs made from copper, even though the spring constant is different because they have different dimensions, therefore they will stretch by different values of x when F is applied. As long as they belong to the same material, the Young modulus is going to be constant. The Young modulus is going to be constant. So that is the difference between Young modulus and the force constant. For a force constant, it can be different for the same material for two objects or for example, two wires from the same material but having different dimensions. If I have a very thick wire, for example, and a very thin wire, both made from copper, the force constant for the thick wire is going to be bigger than the force constant for the thinner wire. However, the Young modulus does not depend on the dimensions of the material. Therefore, the Young modulus for these two will be the same, even when the force constants will be different. This therefore means using Young modulus is a better solution, or in finding unknown extension is a better approach than using the spring constant. So using Young modulus is going to be better than using the spring constant for finding unknown extensions, because it's a constant for a particular material irrespective of the dimensions. So the Young modulus is a constant for a particular material irrespective of the dimensions of the material. That's what makes it better to use to find unknown extensions. However, Young modulus can only be applied whenever Hooke's law is obeyed. So you cannot use the approach of Young modulus to find unknown extensions unless Hooke's law is obeyed. So if Hooke's law is not obeyed, then Young modulus is not applicable. It is only applicable whenever Hooke's law is obeyed. Okay, so we have been talking about Young modulus. Let's try to describe an experiment to determine Young modulus. This experiment can be carried out in a class or in the laboratory at your school. So this is a common equation. I think it was 2010. Determining Young modulus. The question is describe an experiment to determine the Young modulus of a material in the form of y. That is a question I quoted in a paper. I think it is 2010, or if not 2010, it is 2011. Okay, so of course the arrangement I expect you to carry out in the laboratory should look like this, where you need a wire. On the wire, you will need to put a reference mark, such as a paper flag, like this one. You can arrange this in the laboratory. You need a pulley. So the wire should run over a pulley, and the wire should be fixed on the other end. So I fixed the wire using the end of the wire is clamped between two wooden blocks on the other end. And of course, I attach masses, or I attach loads on the other end of the wire. So you can put a hook on the other end and you put your masses that side. So remember we want to find Young modulus. In your mind, you have the formula for Young modulus. Young modulus is equal to the force times the original length over cross-sectional area times extension, which is the same as the force times the original length over. To find the area, remember area is pi d squared over 4. So this is going to be pi d squared. The 4 goes up, then times the extension. So we need to take measurements of the original length of the wire. 2, we need to take measurements of the diameter of the wire. If we assume that the diameter does not change much, so we can assume that the original length of the wire remains constant and the diameter remains constant. So to find the force, of course, we are adding weights. So force is going to be m times g. So we shall be adding different masses m as we record different values of E. And what we can do later on is maybe we can plot a graph if we want. Or for a single value of E, we can just find one value of F and one value of E, and we substitute to find one value of capital E, but that will not be reliable. The best would be to plot a graph. So number one, I'm saying we shall measure the diameter D at several points along the wire using a micrometer screw gauge. So we shall measure the diameter, say at this point, measure that point, measure that point. So you find the average value of diameter. That is to improve, or that is to reduce a random error. You take measurements of the diameter at different points of the wire and obtain the average value of the diameter. That one is improving the random error. Number two, we shall now determine the cross-sectional area. Of course, I mentioned cross-sectional area is going to be pi d squared over 4. So I can find the cross-sectional area from pi d squared over 4 after having determined the diameter of the wire. So the cross-sectional area will be determined from pi d squared over 4. Number 3, I said we shall measure the original length, L naught. So we measure D using a micrometer screw gauge because we expect that the wire is going to be thin enough, because a thinner wire will give a greater extension when loaded. If it is very thick, it may give a smaller extension when loaded. So we measure the length L naught of the wire from, say, at the clamped point here, maybe up to the paper flag, up to a fixed point or up to a reference mark. So I can say that this is going to be my original length, L naught. Before loading, or I might have considered these masses as the reference masses just to straighten the wire. So I may now go on adding loads onto this. So these ones will not be considered. I may consider the ones I go on adding as my new loads. So measure the original length L naught of the wire from the clamped end to the reference mark using a meter ruler. So the instruments to be used here are very important. We are using a meter ruler to measure the length L naught. We have used a micrometer screw gauge to measure the diameter. But when we are using the micrometer screw gauge, we take into account that the diameter of the wire may not be uniform throughout. Therefore, we can measure at different points of the wire and we obtain the average diameter. So how do we therefore determine now the Young modulus from those results? So there are two ways of doing this. For a single result, I said you can just substitute. But for more reliable results, then we should have to plot a graph. So measure the extensions or determine the extensions E as the masses M are added to the mass carrier or to the mass hanger. Then I say that the load F or the force F is going to be determined from force equals to M times G, where G is acceleration of free fall. So having obtained F, different values of F, so I have different values of E and I have different values of F. So you have different values of E in centimeters maybe and different values of F in newtons. The next thing would be to plot a graph of, say, F against E. So next is plot a graph. Plot a graph of F against E. Remember the equation was E equals to F L naught over A times E. And I said A might be approximately a constant and L naught is automatically constant. So we are now going to, these are going to be constants. So I will just take them the other side. So it means the Young modulus E times A divided by L naught is equal to F over E. So I make F the subject, it means F is going to be E A over L naught times E, small e. So we are going to plot a graph of F against small letter e. That is, we are going to plot a graph of F against extension. When you compare with y equals to mx, it means the gradient of the graph is going to be EA over L naught. So the gradient of that graph we are going to plot is going to be capital EA over L naught. Therefore, from that gradient, we can now find the Young modulus. So the Young modulus E is equal to the gradient times L naught over A. Just make it a subject. So if the gradient is equal to E A over L naught, so making it a subject will be gradient times L naught, divide this by A. So the gradient is going to be EA over L naught. So the Young modulus is going to be the gradient times L naught over A. So that is how we can obtain a more reliable value of Young modulus. We can change the values of the masses and obtain different values of extension as we calculate different values of F. Then we can plot a graph of F against E. The reason that's why we're plotting F against E instead of plotting stress against strain is because we can assume that the cross-sectional area does not significantly change when a material is stretched. The change in the cross-sectional area is very small and negligible. So that is how we obtain the Young modulus. But we need to note a few things when obtaining the Young modulus from that experiment. You can carry out that experiment in your laboratory, in your school laboratory, maybe for copper wires, but they should be extremely thin. But you should consider the following when carrying out that experiment. So the following should be considered when determining the Young modulus. Number one, the wire you use or the wire you choose to use must be as long as possible. A long wire is going to give us a bigger measurable extension. Many times when you take a measurement of a large quantity, the percentage uncertainty is always very, very small. So a long wire is going to give us a large and more measurable extension, which will give us a smaller percentage uncertainty. Number two, it's better use a copper wire. A copper wire is often used. This is because for wires of the same diameter, under the same load, a copper wire will give a larger, more measurable extensions than steel wire. Copper is less stiff compared to steel. So if you choose steel in the laboratory, you may not even get a measurable extension in the laboratory. So it's better use a copper wire rather than a steel wire because copper is less stiff. It will give a larger extension. And I've mentioned that the larger the measurement, the smaller the percentage uncertainty. Number three, when you are carrying out the experiment, make sure the wire has no kinks. That is bendings before even loading. That's why we attached a mass at the other end to stretch the wire so that it is taut. Because if it has kinks, those are the foldings. If the wire you are using has these kinks, instead of stretching, when you load, it just unfolds. When you load it, instead of stretching, these kinks just unfold to give an exaggerated extension. So the wire should not have kinks. The wire should not have kinks in it, otherwise there will be big extensions due to the wire straightening out rather than just stretching. We want it to just stretch, not to straighten out, but to stretch. Therefore, it should not have kinks. Number four, care must be taken that the limit of proportionality is not exceeded. Remember, we only find Hooke's Young modulus from the part of the graph where the stress is directly proportional to the strain, part of the graph where Hooke's law is obeyed. So the limit of proportionality should not be exceeded. This can be checked by removing the load after each addition of the weight. So you remove the load after each addition and see if the wire goes back to its original length when the deforming force is removed. If the limit has not been exceeded, the wire should return to the original length it was before the weight was added. The above method is only applicable when Hooke's law is valid. So that means the limit of proportionality should not be exceeded, because if it is exceeded, Hooke's law will not be valid anymore. So if you want to note that the limit of proportionality has not been exceeded, or if you want to note that the elastic limit has not been exceeded, every time you must remove the load and see if the material returns to its original length. When you watch the past paper questions, you'll understand this in more details. Okay, so here is a summary of what we have discussed under stress, strain, and Young modulus. Stress, strain, and Young modulus. So this table summarizes everything. When you're rushing for an exam, you just look at the table and then you go for the exam. Stress, strain, and Young modulus. So we know what stress is, force over cross-sectional area. You can write F over N. The letter is sigma, units, pascals. Extension over original length, that is strain, E over L naught. Epsilon is the symbol. It has no units, therefore it is not a physical quantity. It's a ratio of two lengths, therefore the units cancel out. Then we have Young modulus is the ratio of stress over strain. And we normally use the letter E. Sometimes students use the letter capital Y, which is fine. The units are the same as those of stress or the same as those of pressure, which would be the pascals. That is a summary of stress, strain, and Young modulus. And then the last part of this lesson, which is very important, is elastic potential energy. In a unit work, energy and power, you may talk about elastic potential energy. But before you reach that, I will still give you a clue, because here we are considering deformation of materials. And many times when materials are deformed, the energy stored is called elastic potential energy. I think that's what you mentioned in IGCSE. So let's talk about elastic potential energy. So let's consider a catapult on which an object is stretched, is attached to this elastic band and stretched. Of course, we notice that when the stretching force is removed, the object is made to move. That means when we were stretching, we were storing energy in the elastic band, and that energy is given to the object when the stretching force is removed. So it's like energy is being converted from a certain form of energy which was stored, which we are going to call the elastic potential energy. It is the one which is stored when the elastic band is stored, is stretched. When you look at the first animation, the object rolls down the slope and it compresses the spring. So when the object compresses the spring, energy is stored in this spring, which energy is also going to be called elastic potential energy. So it's like the energy stored in a stretched material, the energy stored in a compressed material. In general, we can say the energy stored in a deformed material is going to be called the elastic potential energy. Sometimes it is called the strain energy. Strain energy. So when you stretch or compress a material, you are doing work. This is because you have to apply a force, and the force causes the material to either extend or to be compressed in a particular direction of the force. So when we stretch the catapult, the material stretches in the same direction of the stretching force. When the object on the slope compresses the spring compresses in the direction of the object. So we are doing work because the force is causing an extension in the direction of the force. The energy which is stored in a deformed material is what we call the elastic potential energy. The energy stored in a deformed material is called the elastic potential energy. Or sometimes it will be called the strain energy. By the way, this is not the energy in a stretched material. It is the energy stored. There's a reason as to why I'm saying it is stored. It is stored because it becomes useful when the deforming force is removed, so that now the elastic potential energy which was stored is converted into other forms such as kinetic energy and so on and so forth. So that is what we mean by elastic potential energy, the energy stored in a deformed material. Let's understand elastic potential energy in more details. So if the material has been strained elastically, what does that mean? Remember, for elastic deformation, I said when the deforming force is removed, the material returns to its original length. So the elastic limit has not been exceeded. So all the energy which has been stored is going to be recovered or is going to be converted into other forms. For example, if we stretch a catapult, for example, an elastic cord for the catapult, and we have stretched it elastically, we expect that all the energy which was stored or all the work done in stretching must become kinetic energy. So all the energy can be recovered if the material was strained elastically or deformed elastically. But if the material is plastically deformed, if a material has been plastically deformed, some of the work done in deforming the material is not going to be returned. Some of the work done will go into moving atoms past each other, making the atoms slide past each other so that they reach in new places, in new positions. And therefore, since the atoms do not go back to their original length, that energy or that work done is not going to be recovered. So what would happen essentially would be the material simply warms up. In other words, the energy which is wasted in that case when the material is deformed plastically becomes heat because the material therefore warms up. That's what we call elastic potential energy. So if the material is deformed elastically, all the energy becomes converted to other forms. But if the material is deformed plastically, some of the energy that was used in deforming the material is wasted as heat, or it becomes internal energy in the material That's why the material may become warm. So that is what we are talking about as elastic potential energy. Okay. So the elastic potential energy we are talking about here is actually going to be equal to the area under the force extension graph in the linear section where Hooke's law is obeyed. In this section, we know that the extension is directly proportional to the applied force. Remember, when the material is stretched, work is done, and the work is done because the force causes an extension in the direction of the force. The force causes an extension in the direction of the force. That means if I have a graph of force, if I have a graph of force against extension, at that point where the force is directly proportional to extension, Hooke's law is obeyed. And if we don't go beyond the elastic limit or the proportionality limit, it means the force is directly proportional to the extension. And the elastic potential energy is going to be equal to the area under this section here for the force extension graph. The work done in stretching the material or deforming the material is equal to the area under this extension force graph up to the proportionality limit. And if we try to find, by the way, it is always the area with the extension axis. If it is a graph of extension against force, it will be the area with the vertical axis. Now that is a graph of force against extension, it is the area with the horizontal axis up to the point where the proportionality limit is. So we can say area, the elastic potential energy, sometimes I put a P subscript P here to mean elastic potential energy, is going to be called the area under this graph. And this being a triangle, it is going to be a half F times E. It is going to be a half F times E. But I also want you to recall from Hooke's law. In your mind, you recall from Hooke's law that F is equal to K times E, where E is the extension in this case. I'll come back to that shortly. So, if we can find the elastic potential energy from the area under the graph, then from the definition of work done and the work done when extension is proportional to the force is going to be, the work done when extension is directly proportional to the force is simply going to be the elastic potential energy from the definition of work done. So from a graph, whenever we have a graph of force against extension and we want to find the elastic potential energy, we just find the area under the graph up to where the straight line stops. That is the elastic potential energy. So we can also find elastic potential energy from the definition of work done. And the work done when extension is proportional to force is the elastic potential energy. It's only when the extension is proportional to the force. That's why I considered the straight line section of the graph. And from work done equals to force times distance, that is in the direction of the force. Because the force is not constant, it keeps on increasing, then the average force is going to be the most useful force here. The effective force causing an extension E is going to be the average force. And since the force increases from 0 to capital F, then the average force is going to be 0 plus F divided by 2, which is F over 2, that is the average force. Therefore, the elastic potential energy is still equal to a half Fe. The elastic potential energy is going to be a half Fe because it's the average force times the distance, which distance is the extension. We need to note something here which is very important. The total work done in stretching the material or compressing a material is always going to be the total area under the force extension graph. Sometimes or most of the times the graph is a straight line where we can easily find the area under the shapes. It could be a triangle, rectangle, and so on and so forth, or trapezium. But if the graph is not a straight line, then you must find techniques of finding the area under the graph, either by counting the squares or using some other techniques that you might have mentioned in kinematics when we're dealing with the velocity time graphs. If the graph is a straight line, you can find the area from a shape. If the graph is a curve, for example, it is just a curve like this one here, then you have to find techniques. For example, some people would say, okay, I will first draw off a triangle here at the bottom. I find the area of this triangle. Then I count the number of squares here, and I multiply the number of squares here with the area of each small square. I also add the number of half squares times the area of half a square. So that when I sum up all this, I get the total area under this curve, which will be the total work done in stretching or compressing the material. But if it is elastic potential energy alone, it is area, what I mean, it is the area under the straight part or the straight section of that graph. So from what we have mentioned, that elastic potential energy is a half Fe, where F is the force and E is the extension, then we can express elastic potential energy in different expressions. So the elastic potential energy relates to the elastic potential energy or strain energy strictly relates to the elastic part of the graph. So we can only consider the linear section. Remember I said the elastic limit is very close to the proportionality limit. But of course, for learning purposes, we exaggerate the space between the proportionality limit and the elastic limit. But the elastic limit is essentially very close next to the proportionality limit. So if we recall from Hooke's law that force is directly proportional to extension and the force is equal to K times E, as we have mentioned earlier on, where K is the spring constant or the force constant and E is the extension, then the elastic potential energy, which is given as a half Fe, can also be a half Fe times a half F, where there is F I'm putting Ke, then times the extension E. And when you simplify that mathematically, it means the elastic potential energy can be a half Ke squared. Also, I can remove E because if I make E the subject, E is going to be equal to F over K. So when I substitute for E in this equation, elastic potential energy is going to be a half Fe squared over K, which is going to be that expression. So sometimes, like I mentioned, sometimes you'll see X used for extension instead of E. So you'll find elastic potential energy written as a half Fx or a half Kx squared or a half F squared divided by K. So this could still be elastic potential energy. I think we have explored much about elastic potential energy, stress, strain, and Young modulus. The only thing we have not done is we have not done any examples. So let's do a few examples here. Examples. Let's do an example here. Let's consider the figure which has been shown here. So the figure above shows a force extension graph for a piece of metal. Find elastic potential energy. Remember I said the elastic potential energy is for the straight line part of a force extension graph where Hooke's law is obeyed. Find elastic potential energy when the metal is stretched to its elastic limit and the total work that must be done to break the metal. So elastic potential energy, I just find the area under this part here. For total work done, I find the total area under this graph. So this is a triangle, so this is going to be a half times F times the vertical times the height times h, which is 5 times 10 to the power of minus 3. That is elastic potential energy. But for total work done, this is a rectangle, so this is 5 and 30 is 25. 25 times 10 to the power of minus 3 times the vertical, which is 20. So if I want total work done, I'll add this area here to this area here. Okay. So in our solution, the elastic potential energy when the metal is stretched to its elastic limit is given by the area under the graph up to the proportionality limit. And the graph is a straight line up to x equals to 5 millimeters or 5 times 10 to the power of minus 3 and F equals 20 newtons. And so it means that the elastic potential energy is the area under the line O to point A. So this is, by the way, equivalent to using a half Fx which is a half, times 20 times 5 exponent minus 3, and it gives us 0.05 joules. If I wanted total work done, then I said I will find total area under that graph. And since we have a triangle and a rectangle, I just sum up the two. And this gives us 0.5 plus 20 times 25, which gives us 0.55 joules. So that is the total area under the graph, which is the total work done. Okay. So now we have a self-check. I'll be giving you a hint wherever possible. I'll do a few of these questions and I'll leave you to do the rest. A spring has a force constant of 4,800 newtons per meter. So that is K. Calculate the elastic potential energy when it is compressed by 2 millimeters. So this is going to be X. So we want to find the elastic potential energy. Remember, we know that elastic potential energy is going to be a half Fx, which is the same as a half Kx squared, which is the same as F squared over 2K. So you have all that. So it depends on what you have. So here I'll just simply, we want to find elastic potential energy. So I'll just substitute in K and X. So this will be a half times K, which is 4,800, times X, which is 2 times 10 to the power of minus 3, and this is going to be squared. Let me check. Some of these answers are for my students, so I've never checked them. 0.5 times 4,800 times 2 exponent minus, it is 2 exponent minus 3, but this is squared. So this answer I think is correct. You can also verify with your calculator. Number 2, a force of 12 newtons, so this is F, extends a length of a rubber band by 18 centimeters, so this is going to be extension X. Estimate the energy stored in this band. So because we have F and X, we shall use a half Fx. So energy is going to be a half times 12 times 18 times 10 to the power of minus 2, but this should be squared. So this is 12 times 0.5 times 18 exponent minus 2, but this is squared. So this is giving me 0.19 joules. You can also verify. Number 3, explain what is meant by the phrase, a material is extended elastically. So here we have said, when the deforming force is removed, the material returns to its original length. That one is easy. Number 4, calculate the spring constant. So we want to find K. For a spring which extends by a distance 3.5 centimeters, so this is X. When a load of 14 newtons, so this is F, is hung from its end. So here you just use Hooke's law. The constant K is equal to F over X. So this is going to be 14 divided by X, which is 3.5, times 10 to the power of minus 2. I think that answer is correct. Let me check. 14 divided by 3.5 exponent minus 2. So I think that is correct. Number 5, a steel wire extends by 1.5 millimeters. So this is X. When it's under tension of 4.5 newtons, so this is F. Calculate part A, the force constant. So we want to find K. K is going to be F over X. I will not check that. Then B, the tension required to produce an extension of 1.8 millimeters. Assume that the proportionality limit is not exceeded. So the constant is going to remain the same. If this constant is correct, then we just use the constant and this extension to find the tension. They want us to find the force. The tension to produce this extension. So this is going to be X and this is going to be F. We want to find F. We have X. Of course, the constant remains the same, so you can verify that. So I'll just go through some of these self-check questions. You can pause the video and you try to solve them and see if the answers given are correct. A spring has spring constant 65 newtons per meter, that is K, and it is extended elastically by 1.2. So this is extension. Calculate the strain energy. So they want you to calculate the elastic potential energy. So you can verify and see if that is correct. A wire has a force constant. So this is K, 5.5 exponent 4. It is extended elastically by 1.4 millimeters. So this is X. Calculate the strain energy. So they want you to find E. You can verify and see if that is correct. A rubber band has a force constant 180 newtons. So this is K. The work done in extending the band is 0.16 joules. So this is the elastic potential energy. Calculate the extension of the band. So they want you to find the extension of the band. So remember, elastic potential energy is equal to a half times F times X. They have given us F. They have given us E. You should be able to find X. An elastic band of area of cross section 2 millimeters squared has an unstretched length of 8 centimeters. So this is area and this is unstretched length. So this is original length L naught. When stretched by a force of 0.4 newtons, its length becomes 8.3 centimeters. So this is going to be the new length. Calculate the Young modulus. So remember, Young modulus is equal to stress divided by strain, which is the same as force times the original length over area times extension. So this is going to be equal to the force, which is 0.40. Original length is 8 times 10 to the power of minus 2 divided by area. We have to change the area from millimeters squared to meters squared. So this will be times 10 to the power of minus 6. Remember, 1 meter is 1,000 millimeters. So that means 1 meter squared is 1,000 millimeters also squared. So that means 1 meter squared is equal to 1 times 10 to the power of 6 millimeters squared. So if we move from millimeters back to meters, it will be power negative 6. So this will be 2 times 10 to the power of minus 6. Then times the extension. To find the extension, we get the original length. We get 8.3 minus 8, which is going to be 3 centimeters. So this will be 3 times 10 to the power of minus 2. So I'll check with my calculator. 0.4 times 8 exponent minus 2 divided by 2 exponent minus 6 divided by 3 exponent minus 2. Yeah, I think this answer is correct. One, two, three, four, 5. I think this is 5. You can check and verify. I think that is 5. So I think that is 5. I can check it again. 0.4 times 8 exponent minus 2 divided by 2 exponent minus 6 divided by 3 exponent. So yeah, it is 6 because this is 0.3, not 3. So this is 0.3. So it is power minus 6. I mean, it is power 6 because this is 0.3 times 10 to the power of minus 2. The extension is 0.3. Okay. A steel wire of diameter 1 millimeter and length 2.5. So this is diameter, this is original length. Is suspended from a fixed point and a mass of weight 45 newtons. So this is going to be F. which is the load, displacement from its free end. The Young modulus of the wire is 2.1 times 10 to the power of 11 pascals. So this is going to be capital E. Assuming that the proportionality limit of the wire is not exceeded. So that means Hooke's law is obeyed. Calculate the applied stress, the strain, the extension of the wire. So I'll just give you formulas here. Stress, for the stress is equal to force over area. Remember, the area is going to be pi d squared. So this is going to be 4f over pi d squared since they gave us the diameter. So this is going to be 4 times f divided by pi times d. D is 1 times 10 to the power of minus 3. But this should be squared. So when I press my calculator, it's going to be 4 times 45 divided by pi into 1 exponent minus 3, but this should be squared. So I think this answer is correct for 5.7 power 7. Then the strain is equal to extension over original length. That is if we have the extension. We have the original length, we don't have the extension. However, we also know that stress is equal to is equal to Young modulus times strain. So this means I can say strain is going to be stress, which is 5.7 times 10 to the power of 7, divided by Young modulus, which is 2.1 times 10 to the power of 11. I think this answer is correct. Divide by 2.1 exponent minus 11. So this answer is correct. Then the extension of the wire. So since strain is extension of original length, so I'll say extension is going to be strain times original length. So that is 2.7 times 10 to the power of minus 4, then times the original length, which is 2.5. 2.57 times 2.5. So I think this is correct. A wire of length 2 meters and diameter 0.4 millimeters is hung from the ceiling. Find the extension. So this is the original length. This is diameter. Find the extension. So this is x in the wire when the weight. So this is going to be the force 100 newtons is hung on it. The Young modulus is given as this. So I'll just write here the formula. Young modulus E is going to be, so E is equal to force original length over area times E. But they gave us diameter, and remember area is pi d squared over 4. So this is the same as 4 f L naught over pi d squared times E. So you can make E the subject and substitute. So E, small e, is going to be equal to 4 f L naught divided by pi d squared times capital E. They wanted us to find extension E or X. I can use X for that matter. So F is known, L naught is known. D, you just change D from millimeters, so it will be 0.4 times 10 to the power of minus 3 to change it to meters. The Young modulus is known, so you should just check that answer and see. I expect that is correct. The Young modulus of steel is 1.9 exponent 11 pascals. The Young modulus of copper is 1.2 exponent 11 pascals. The steel wire and the copper wire each have the same cross-sectional area and length. The two copper wires are each extended by equal forces. Use the definition of Young modulus to determine the ratio extension of copper wire over extension of a steel wire. So remember Young modulus, they said they have the same area, the same length, the same force. So Young modulus equals to force times original length over area times extension. So it means if F, L, A are the same, I'll say E is equal to a constant over E or over X, where X is the extension, because F, L naught, and E are constant. So I'm going to come up with two equations only. For copper, I will say Young modulus for copper is equal to a constant over extension X for copper. So that means X for copper is equal to K over Young modulus of copper. That also means X for steel is going to be K over Young modulus for steel. So I want X for copper over X for steel. So I'll just divide the two equations. X for copper over X for steel. Till we are going to get the reciprocals. Here X for copper is K over EC and X for steel is K over ES. So ES goes up. So it becomes ES over E copper. I'm saying I'm getting K over E copper divide by, so I get the reciprocal, E steel over K, where K cancels. So this is going to be a Young modulus of steel, which is 1.9 times 10 to the power of 11 over 1.2 times 10 to the power of 11. I think this is correct. 1.9 divided by 1.2. So that is 1.6. Two wires are each extended by a force. Both wires obey Hooke's law. On the figure below, sketch a graph for each wire to show the variation with the extension of the force. Label the line for steel with the letter S and the line for copper with the letter C. So we have seen that extension for copper is equal to 1.6 times extension for steel when we use the same force. What does that mean? It means copper is less stiffer. The same force will cause a bigger extension for copper than for steel. So I'll draw two straight lines, but the one for copper will be at the bottom because it extends more. Because copper extends more many times than steel, so this will be copper and this will be steel. Steel is of course stiffer. That's why we said we can't use it for determining Young modulus in the laboratory. Okay. A copper wire of diameter 1.78, so this is the diameter, and length, so this is the original length, 1.4, is suspended from a fixed point and a mass of weight 24 newtons. So this is going to be the force. Is suspended from its free end. The Young modulus of the material is 1.1 times 10 to the power of 11 pascals. So this is Young modulus, which is E. Assume that the proportionality limit of the wire is not exceeded. Calculate the applied stress, the strain, and extension of the wire. So here I'll just state the formulas. Stress is force over area. They gave us diameter, so area is pi d squared over 4. So this becomes 4f over pi d squared. That will give you the stress. Then the strain is extension of our original length, but we don't have extension, but we have the stress and the strain. So the stress, we have the stress and Young modulus. So strain is going to be equal to the stress divided by Young modulus. Then the extension, so if you have the strain, then extension is going to be the strain times the original length. I think that one is direct. You can check those answers. The figure shows force extension graphs for two pieces of polymer. For each of the following questions, explain how you deduce your answers from the graphs. State which polymer has the greatest stiffness. So the greatest stiffness, this is going to be A. And why A? Of course, a bigger force is causing a smaller extension, so that is stiff. State which polymer requires the greatest force to break it. It is still going to be A. Because it is very stiff, it requires a great force to break it. The line is going to the line continues to a higher force value, so it is very stiff. It requires a greater force to break it. State which polymer requires, in other words, A has a greater gradient, so it has the greatest stiffness, has the greatest constant, so it requires more force to break it. State which polymer requires the greatest amount of work to be done in order to break it. So work to be done is going to be A, because work done is going to be the area under the graph. So if you compare that area with this area here, you may find that the area under A is smaller than the area under B. So the answer here is going to be B, because the work done to break the material will be the area under the graph. Yeah, I think those answers are correct. For A, the stiffness is A. It has less extension per unit force. A requires a greater force to break. B requires a greater amount of work done to break because of the larger area. Okay. For each of the material whose stress strain graphs are shown in the figure below, deduce the value of Young modulus and the ultimate tensile stress. What do we mean by ultimate tensile stress? So the ultimate tensile stress is the maximum stress that a material can withstand before it breaks. That's what we call the ultimate tensile stress, or the breaking stress. The maximum stress that a material can withstand before it breaks is what we call the ultimate tensile stress. So identify which material is stronger, give a reason for your answer. So which material is stronger? The material which is stronger must be having a bigger ultimate tensile stress. So identify which material is stronger and give a reason for your answer. So we have material A, we have material B, and we have material C. So a material which is stronger is going to be A, because it has a greater tensile stress. So that is A. Then give a reason for your answer. It has a greater ultimate tensile stress. And they said deduce the values of the Young modulus of the and the ultimate tensile stress, or the breaking stress. So for A, the Young modulus is going to be the area under the graph, which is 150. I mean the gradient of the graph, which is 150 divided by 0.3. 150 divided by 0.3, because straight line, for a straight line, the Young modulus is the gradient. So we have 150 divided by 0.3, which is going to be 50. Sorry, this is, of course, this is a ratio, so 0.3. This is expressed as a percentage. So I'll divide again this by 100, so divide by 0.003, I think. But remember, this is times 10 to the power of 6. So you have 150 times 10 to the power of 6 divided by 3 times 10 to the power of 3. So it becomes gigapascals. So it becomes 50 gigapascals. Then for C, it is going to be 100 divided by 0.4, which is going to become 100 divided by 0.4, which I think is going to be 25 gigapascals. 50 divided by 0, I think that is 25. And then the ultimate tensile stress, the maximum breaking stress, I think the maximum breaking stress here will be approximately 100, and for B it is approximately this one here. I think this is very close to 100 and around 130, about 130, the ultimate tensile stress. This is 150 130. Then for C, I think it is 100 by 0.4, which is 25, which should be 25 gigapascals. And the ultimate tensile stress is going to be 100. I think those are the answers. You can verify them. Yeah. For A, we have 50 gigapascals and 150 megapascals as the ultimate tensile stress. For B, actually this is for C, not for B. Oh, this is for B. I think I messed up these. For B, yeah, for B, remember for Young modulus, you take this straight line part, it is 100 divided by 0.1, which is 100 gigapascals. And the ultimate tensile stress is 130, where it breaks around here. Then for C, I didn't add C. C is going to be 100 divided by 0.4, which I think is going to be 25. I think it's 25 gigapascals. And the ultimate tensile stress is going to be 100 megapascals. This value here for stress, the maximum stress that a material can withstand before it breaks. That is the ultimate tensile stress. Okay. So a few things we need to note before we wind up this. Note, the strength of a material tells us about how much stress is needed to break the material. And the maximum stress a material can withstand before it breaks is what I've been calling the ultimate tensile stress. The maximum stress that a material can withstand before it breaks is the ultimate tensile stress. The term ultimate is used because it is the top of the graph. That's why I've been choosing the values on top of the graph from the previous example. So we use ultimate because it's the top of the graph. For a brittle material, that is a material which breaks without giving warning, the ultimate tensile stress is at the breaking point. It is exactly at the breaking point because the material stretches up to the breaking point for a brittle material. And if a big force only produces a small extension, we have already said that the material is stiff. If a big force causes a very small extension, the material is stiff. And if a big force causes a small extension, then the Young modulus is going to be a big value because E is equal to F, original length over A times E. If the force is big and the extension is small, it means the Young modulus is going to be big. And if a very small force produces a big extension, the material is not very stiff, it is easier to stretch, and the value of Young modulus will be smaller. So it means a material which is easier to stretch is less stiff, even its Young modulus is smaller because even its force constant is also smaller. So we should note that very carefully. Okay. List the materials in the table below from the stiffest to least stiff. Which of the nanometals in the table is the stiffest? So we are listing them from the stiffest. So a material which is very stiff has a bigger Young modulus. So they said list the metals. So we have iron, steel, those are the metals. You may not really consider concrete as metal because concrete is a mixture. So it is going to be from the stiffest, that is steel, followed by iron. Or maybe you can add concrete. So we'll say steel, iron, and maybe concrete, although concrete is a mixture. Then that is the list from the stiffest to the least stiff. Which of the nanometals in the table is the stiffest? So the nanometal, which is the stiffest, is automatically glass. Or you can consider concrete because concrete is a mixture anyway. It has gravels, it has stones, it has metals. Then I quoted the past paper question here, which I quoted from, I think that is October, I think that is 2010. A student measures the Young modulus of a metal in the form of a wire. Describe with the aid of a diagram the apparatus that could be used. Of course, we have already seen the apparatus that could be used. So you need a wire. Of course, you need a ruler to take measurements to measure the original length, L0. You should clamp the wire on one side. And you need a reference marker or a paper flag. And you need a mass hanger where you're going to be putting loads and a pulley over which the string runs. So we have carried out that experiment. So that is the diagram. It carries 3 marks. You can just do a simple diagram like that one. Then describe the method used to obtain the required measurements. So I've given here marking points for the method. Because we want to find the Young modulus, it is force times original length over cross-sectional area times extension. So to find, we have to measure the original length, that is using the ruler. To find the cross-sectional area, we need pi d squared over 4. We must measure the diameter using a micrometer screw gauge. Then we must measure, to find the extension x, we must measure the original length, and we must always measure the new length. So we get the new length minus the original length to find the extension, that is using the ruler. Then we must record the masses, and of course we determine the weights from F equals to mg. That is easy. Then measure the diameter. Of course, I mentioned that to measure the diameter, we measure the diameter at different points, at several points along the wire, and obtain the average. That will be the best diameter. And by the way, I also mentioned that you should also ensure that the elastic limit is not exceeded. That's why you should check that the wire always returns the original length. Every time remove the load and see that the wire returns to the original length. So you had to choose to pick out a few of these points to get 4 marks. So I gave 1, 2, 3, 4, 5. So you had to pick out at least 4 of these points. You say measure the diameter using a micrometer screw gauge and measure the diameter at several points along the wire and obtain the average. Those are 2 marks. Measure the original length of the wire using a meter ruler. Those are 3. Now 3. Measure the initial and the final length of the original length of the wire and the final length of the wire using a meter ruler and subtract to find the extension. Those will be 4 marks. Measure and record the mass and then obtain the weight from F is equal to mg for each extension. Then every time I mention that we should always remove the load to check that the wire returns to its original length so that the elastic limit is not exceeded, because if the wire does not return to its original length, then we cannot obtain Young modulus, because Young modulus is only obtained where Hooke's law is obeyed. So Hooke's law is not obeyed if the wire stops, if the material does not return to its original length. It means the elastic limit was already exceeded, and also the proportionality limit must have been exceeded. The last part of this question was to describe how the measurements taken can be used to determine the Young modulus. So this is now analysis. So having determined the extension from the initial and the final readings, that is extension is equal to the new length minus the original length, you could plot a graph of force against extension, and from Young modulus equals to force times original length over area times extension. We are calculating the area from pi d squared over 4 as I have mentioned. So you have measured the extension, you have calculated the area, you have calculated several extensions, you have calculated the area, then you have different values of F. So we now plot a graph of force against extension. And I've already mentioned this in the previous slides. So from the graph of F against extension, we saw that the gradient of this graph, because F is varying with extension E, the gradient of the graph was E. When I make F the subject, F is equal to capital E, capital A times small e divided by L naught. So we saw that the gradient was EA over L naught. So the gradient was equal to EA over L naught. So you just make E the subject. So calculate E from, either you calculate E from F L over EA, that is what I mentioned here, or you just obtain the gradient. And the gradient is equal to EA over L naught, where it means Young modulus is going to be the gradient times the original length divided by the cross-sectional area. So that is the analysis part. So you had to give at least 4 points to score this for. So this question was about 11 marks. I think that is the end of deformation of solids. Do not forget to watch the solved past paper questions. Those would be the most important questions to make you confident with this unit. Until next time, bye-bye.
At 29 and I find myself wondering what did happen to the last 10. I ran away with my life, fast forward, never turn back again. It's kind of funny that the more we waste time, the more we need to set the rewind. And 19 was the year I had to leave you, but now I'm seeing all the signs. Is this really happening? I can't believe it's true. I'm just as surprised as you. Is this really happening? I can't be too sure, but one day I'll be yours again. Life has come walking and dancing. The other heaven is something from heaven. I sit here looking for an answer. Really big question, this is the last chapter. You give me this whole heart today. Without you, I never could have moved away. But now I see what you teach. I never leave. I always should have stayed. Yeah. Is this really happening? I can't believe it's true. I'm just as surprised.